class here in just a second. We're on the second day of section 2.4, and we have the real zeros of polynomial functions. We had a pretty good start on talking about those with the long division and division algorithm, and today we're going to talk more about factoring as far as use the remainder and the factor theorems, and using the rational zeros theorem and finding upper and level bounds. We should be talking about both of those today, which makes a person wonder, why do we have a third day on this? And that would be because there are an infinite amount of polynomials that we could look at. So we need to experience a lot of different types of polynomials so that we can find their zeros. And we were at the bottom of this page. Where we had just talked about how synthetic is an option if we have the x minus k factors. So this one has some already broken down, and it says the real zeros of polynomial functions are either rational zeros or irrational zeros. And remember, the root word of rational is ratio, which means a fraction. And we can write integers, 3 can be written as 3 over 1 as a fraction. So those are the ones that we find by factoring. Everything works out nice, it's perfect, and we can find those easily. The irrational zeros, we usually don't factor, and here's what I mean. If we have 4x squared minus 9, we know that. We know that that's the difference of two squares, and we write it as 2x plus 3, 2x minus 3, and we find those zeros as negative 3 halves and positive 3 halves. But if we have x squared minus 2, well, that's not one of our factoring patterns. And we would think, okay, so I need two numbers that multiply to negative 2 and add to 0 since there's no middle term. And that doesn't work. So what we would do is set it equal to 0 and solve it. So we would add 2 to both sides, and then we'd take the square root of both sides. Now, we don't usually say, okay, now I'm going to take this and I'm going to write it in its factored form, which would be x plus the square root of 2 and x minus the square root of 2. But we could. And the square root of 2 is irrational. If you put the square root of 2 in your calculator, it doesn't stop. There doesn't seem to be a pattern to that. So, like I said, usually we'll solve it with some different manner. We'll find the zeros some different way. And then we could always put it back in factored form if we need to. But algebra is about being able to find what you can find on your own. And so even if we can't factor it, one of our old-fashioned factoring ways, that doesn't mean we give up. We keep trying and try to find some answers, some solutions for the problems. And that's really what this section is about, finding all of those solutions in any way possible. So we get to the rational zeros theorem, which is one of the things that you studied in Algebra 2. And it says, suppose f is a polynomial function where the degree of the function is greater than or equal to 1. And this is just our standard polynomial here, with every coefficient an integer, and a sub 0 is not 0. So we have a constant in the back. And it says x equals p over q is a rational zero of f where p and q have no common integer factors other than plus or minus 1. Then p is an integer factor of the constant and q is an integer factor of the leading coefficient a sub n. So here's what this is giving us, and it's actually a little harder to understand than the way it was given to you in Algebra 2. They're trying to say, here are some possibles that you could try. It's not factorable. You took a look at it. You can't figure out what the zeros are. Well, what you can do is you can find possibles by taking all the factors of the constant, which is kind of backwards because it's the last thing we see in the polynomial, and divide it by all the factors of the leading coefficient. And that's going to give us a little fraction. In fact, in most cases, it's going to give us at least two numbers that we'll be able to figure out that we could try to find this. Because back in the days when dinosaurs roamed the earth and I went to high school, we didn't have graphing calculators. And so we couldn't find those rational zeros without actually doing multiple synthetic divisions. And so it's always a good place to start. So this rational zero theorem says, hey, you're looking at it, you're saying, I can't factor this. What should I do? Find some possibles. Reminder, we should always try to factor out that greatest common monomial factor before applying the rational zeros theorem. And again, that's a best practice when we are factoring. We always take out that common monomial factor first. Even if it is just a negative symbol, we need to do that. So that's first step. So back at it now, and it says we're going to find the rational zeros of f of x equals x cubed minus 3x squared plus 1. And again, the first thing we should always try is factoring. So, looks like we have a lot of x's until we get to the 1. We can't pull out a greatest common monomial factor, and we realize, gosh, we don't know how to factor something that looks like that. So we're out of options as far as factoring goes. But the next thing to do would be to use the theorem that we just saw, the rational zeros theorem, and say, all right, possibles. This is a 1. The factors of 1 are positive and negative 1. My leading coefficient is also a 1. The factors of 1 plus or minus 1. So now I actually think about the division that's going on here and realize, well, if I do plus or minus 1 divided by plus or minus 1, I'm going to get plus or minus 1. So I have two options here for possible zeros that I can try. And usually I'll just try the negative first. So I'm going to use negative 1, and I'm going to do synthetic division in the hopes that I can get a 0 for a remainder. So 1x cubed negative 3x squared, but we don't have any x, so I have to put the 0 in as a placeholder, and I need to go all the way to that constant, which is a 1. And again, we go through the synthetic hoping that we see a 0 in that last position. So bring down your leading coefficient, multiply, add, multiply, add, multiply, and add. Well, that's not a 0. Got a remainder there. So this is not going to be a rational 0. Well, there was one more number to try in this, and it was positive 1. So we'll try that with 1, negative 3, 0, and 1, and see if we can get a 0 in that last slot. So bring down your leading coefficient. Outside the box is multiply, inside is add. Outside the box is multiply, inside is add. Outside the box is multiply, inside is add. And those were our two possibles. But they didn't work. We didn't get a 0 in that last position. So that would tell us this one must not have any rational zeros. Now, I would definitely want to check that out on my graphing calculator. So if you have your graphing calculator with you, grab that. And I have it as my first one up there. And while you're punching that in, I'll turn these other equations that we might get to today off. All right. So now if I hit zoom 6, what I'm looking for is where does this graph cross the x-axis? And it's 3 pretty obvious spots. But we just tried the two probable rational ones, and they didn't work. So let's take a peek and see what these are. Second trace, number 2. I'm going to need to be to the left and below the leftmost intercept there and press enter. And then I need to go to the right and above. And here's what I see. My 0 is negative 0.5320889. So I start thinking, is that some decimal that I should recognize as a fraction? It sure isn't a common one. So yeah, that one's probably irrational. Doesn't mean we can't find it. We found it with a graphing calculator. It just means it's not rational. So I still have 2 more to check. Second trace, number 2. And I'm above it to the left and press enter. Below it and to the right, press enter. 0.65270,364. Well, there's another one that I don't recognize. I can't say, oh, that's 2/3, because it didn't come up 0.666 repeating. So yeah, I would say that one's irrational as well. One more. Second trace number 2. This time I'll be below it to be to the left and above it to be to the right. Don't know that one either. 2.8793852. I don't know that one. That is not a common fraction. Now, if you look at the y on this one, this is where some people were getting nervous, and we talked about this after one of the other tests. It says 1e negative 12. It doesn't say 0. What the graphing calculator is doing is kind of cute. It's apologizing because it's saying, hey, I did the calculus on this, and I couldn't get you a perfect 0. But I got you this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. To which we say, you know what, calculator? To us, that's 0, So we can tell it was finding the 0 there. So be careful and watch for that scientific notation. And know that as we're using our 3 decimal places, it's 0 for us. It's as close as we're going to get. So what I just saw was, yeah, none of those came out as fractions that I recognize. And that verifies that this one doesn't have any rational zeros. If you wanted to make just a quick sketch in there, you could certainly do that. But you could write yourself a little note as well. Use the graphing calculator to check. Did not recognize any of those decimals that we saw. So it has 3 zeros, and we know it should have 3 because it was a cubic, and you use that degree to tell you how many zeros that it has. But we're not guaranteed that they're all going to be rational. We're not guaranteed how many irrational we're going to get. In fact, we're not guaranteed that there won't be some that are imaginary. So what our job is to do is to find them. And today we're talking about those rational zeros. We also are going to talk about a few irrational. So example 5 says finding the rational zeros, and it gives us another polynomial. And I take a look at this one, and I'm looking for the greatest common monomial factor. There isn't one. And then I think, okay, well, there's 4 terms. We did learn how to factor 4 terms by grouping, so let me see what I can do here. I can take an x squared out of these. Well, I suppose I could take a negative 1 out of the back. But that's not factorable by grouping. If it were, those 2 factors would be the same. So, again, I've kind of run out of gas on this one. I don't have any factoring methods that I can use. So what I would do is I would use our rational zeros theorem and say, well, this is a 2, so on the top, the factors of 2 for my fraction here would be plus or minus 1, plus or minus 2. And on the bottom, with a 3, I'd have plus or minus 1, plus or minus 3. So what that does is it gives me a list that I can be looking for. So it could be 1 over 1, which would be 1. It could be 1 over 3, plus or minus 1/3. It could be 2 over 1, which is 2. And it could be 2 over 3, which would be plus or minus 2/3. So those are the ones that, if I didn't have a graphing calculator, I would try those until hopefully I found 1. Now, why do I need to find 1? Because this is a cubic, and if I can find just one of those, then it will be down to a quadratic. And we can find the zeros for any quadratic by completing the square. So if we can just get one out of the way, we'll have it. Now, on this one, we would have 2, 4, 6, 8 different numbers that we could try synthetically. And like I said, that's what we had to do in the old days before graphing calculators. But you have a graphing calculator, and so what we would do at this point is we would narrow down our search using our technology, our graphing calculator. Oops. Let me turn that one off and turn this one on. And let me double check it. I just entered those in this morning. So that one is our 3x cubed plus 4x squared minus 5x minus 2. Looks good. Zoom 6. Well, I can see the 3 zeros. I'm just not guaranteed that they're going to be rational zeros. Now, one of the things you might want to do, because you might look at this and say, ooh, it looks like -2 and 1 are nice zeros, is you could use the table feature. And you'll see, oh, look at that, -2 and 1. Those are both good. And you can work from there. Or you can go back and do second trace and find the zeros that way. It's up to you. Now, since I know about -2, 0 and 1, 0, I'm kind of interested in the other one. And that would be the second 0 from the left here. So I'm going to go to the left, which is above it, to the right, which is below it, and enter. And I get -0.333333333, which, you know, eventually the calculator drops off the 3's there. So here's what I know. I know that's -1/3. Now, I think about my list. I just found that we had -2, -1/3, and 1. -2, -1/3, and 1. And they were all there. But I'm supposed to do as much algebra as I possibly can with this. And so what I want to do is work this down a bit so that I can show the algebra. So of those 3, probably the easiest one to do synthetic with would be a 1. And you could pick any of those 3 that we just saw in the graphing calculator. But we want to do a synthetic with this so that we can work it down to a quadratic. So 3, 2, 1, 0, it's in standard form. They're all there. You write down your coefficients. And you go ahead and do your synthetic. And there's what we wanted to see. We wanted to see that 0 in the remainder. Now, I'm supposed to show as much algebra as I possibly can. You know, using that graphing calculator, it's great to use it as a helper, but we have to show the math behind it. So what I want to do is see what I have left. Remainder constant x squared. I have 3x squared plus 7x plus 2, and I still want to find those other 2 zeros, and I want to find them algebraically so I can show that I know these are working. So that would mean I want to try and factor. Now, it's not just a want to try. I know I can factor because I saw the rational zeros earlier when I used my graphing calculator. So I realize there's no greatest common monomial factor, and there's nothing special about this. It's not a perfect square trinomial. I'm going to need a 3x and an x in order to get a 3x squared. And in the back, I need to multiply to 2, and somehow outside times outside plus inside times inside has to add to 7. Well, if I put the 2 here and the 1 here, outside times outside will be 6x, and inside times inside will be 1x, and that'll give me 7. So now I can keep going, and having this equal 0 is important here because that says, hey, I remember exactly what I was supposed to do, which is find the zeros. And then from here, probably most of you would just be writing down, this is -1/3, and this is -2. But now, let's make our answer reflect what we just found. Our answer was about the zeros. So we would want to write down 1, 0. We found that one synthetically. And then -1/3 and, oops, -2. There we go. -2, 0. for our other zeros. So this is a summary of what we found. We knew we were supposed to find the zeros. We found one of them with the aid of the graphing calculator, but we verified it synthetically. So this is the algebra to support the fact that that one works. We can't just say, hey, the graphing calculator told me that. I saw that on the graphing calculator. We have to show the algebra behind why we know it works. Because, I don't know about you, but I've punched stuff wrong into the calculator before. And if you do that and you don't do any checking algebraically, you're never going to know that you put it in there wrong. So we have to show that algebra. Now, we've got 3 of them. It was a degree 3 polynomial, and we're done. There they are. This one had 3. So we encountered 2 different types of problems so far. We encountered one polynomial that did not have any rational zeros, and then we encountered a cubic where we could find all 3 of those rational zeros. Now this extra example says, let's think backwards. If you had to write an equation and you want to put it into a computer to make something appear, how could you make that happen? And this is important as we start thinking about, well, everything uses technology nowadays, especially during COVID. How do you make things appear on the calculator? This is how you think about them. So we want to write a polynomial function of degree 3 with leading coefficient of 2 and zeros of 5, 4, and negative 1. So here's the thought process. Degree 3, not going to be a problem. They told me the 3 zeros. But we haven't made a leading coefficient of 2 before. Well, start with what you know. What we know is they want a polynomial function, so we're definitely going to name that with function notation. We're going to think about the fact that all of those zeros came as factors, as linear factors, so it must have been x minus 5, x minus 4, and x plus 1 that were the factors. That's the only way you'd get 5, 4, and negative 1 out. And then we'd multiply this out. And because multiplication is commutative, we can do this in any order. So I would tend to leave the x plus 1 in the front because that's the easiest one to distribute. And I would multiply the x minus 5 and the x minus 4 together first. Now, if you do it right, it doesn't matter which 2 you do first. But you just have to be careful. This is another one where it's better to be a little bit slower with it to make sure that you have it right. So when I multiply the x minus 5 and the x minus 4, I'm getting x squared minus 9x plus 20. And now, this is when I'm happy that I kept the easiest one. The x plus 1 doesn't have any negatives in it as the last one to multiply through, because I have to multiply everything by x and multiply everything by 1. So multiplying by x, we have x cubed minus 9x squared plus 20x. Multiplying by 1 is nice and easy. And then we can go ahead and combine like terms. And let's all double check at this point before we start talking about that leading coefficient piece. F of x equals x cubed minus 8x squared plus 11x plus 20. So now, that would be perfect if it had just said, write a polynomial function of degree 3 and here's the zeros. But it didn't. It said it needs to have a leading coefficient of 2. So I think, well, what can I do to that so that the leading coefficient would be 2, but the zeros aren't going to change? And I remember that if we have a 2 outside of our factors, the 2 doesn't affect my zeros. My 0 here is going to be a negative 1. The 2 had nothing to do with that because the 2 doesn't have an x with it. So that would mean if I multiply all of these terms by 2, I'll have a leading coefficient of 2, but I won't have changed any of the zeros. So that's what I have to do. So I'm going to give it a new name where I multiply each of these terms by 2. And so that people can follow this in the notes, I'm just going to do this. Because working backwards, if we had to factor this, the first thing we would do is take a 2 out of all of that. So I've got g of x equals 2x cubed minus 16x squared plus 22x plus 40. And writing them, like I said, that's an important real-life skill, being able to write your polynomial functions. Alrighty, off we go. Another part of our objective, which we didn't get to yesterday, was upper and lower bounds. And we've actually talked about this a little bit when we talked about boundedness, but we didn't talk about the math behind it. So we narrow our search for real zeros by using a test that identifies upper and lower bounds for real zeros. A number k is an upper bound for the real zeros of f if f of x is never 0 when x is greater than k. On the other hand, a number k is a lower bound for the real zeros of f if f of x is never 0 when x is less than k. So, if c is a lower bound and d is an upper bound for the real zeros of a function f, all of the real zeros of f must lie in the interval between c and d, including c and d. So, here's what they're saying. They're saying if we know those are the zeros, they lie between the x values of c and d. But we're also going to talk about a way to check and make sure you've found them all. You know, with this one, it just says y equals f of x. We know there are 1, 2, 3, 4, 5 zeros, so we'd be saying probably a fifth degree polynomial, a quintic there. But we don't know that, so that means we have to figure out, is this it? Are these the only zeros? Does this blue graph come back around and touch the x-axis, cross the x-axis again? So this is the upper and lower bound test that we'll be using. Let f be a polynomial function of degree n greater than or equal to 1 with a positive leading coefficient. Suppose f of x is divided by a linear factor, x minus k, using synthetic division. So it's important with these that we know that we have this broken into those linear factors, because we're going to use synthetic. If k is greater than or equal to 0, and every number in the last line is non-negative, so it can be positive or it could be 0, then k is an upper bound for the real zeros of f. So, if we get done with our synthetic for k, and we find only positives or zeros in that last line of information, then k is actually an upper bound. We found the biggest zero that it could possibly be. We found the interval for it. And then if k is less than or equal to 0 and the numbers in the last line alternate non-negative and non-positive, then k is a lower bound for the real zeros of f. So that means we have the lowest number that we could use where there won't be any more zeros to the left of that number. So this is how we're going to check and make sure we have them all, which again is kind of silly because we're going to see what the polynomial is and we know how many zeros it should have. Except when we have imaginaries, then we'll know for sure. So example 6 says, establishing bounds for real zeros, prove that all of the zeros of f of x equals 2x to the fourth minus 7x to the third minus 8x squared plus 14x plus 8 must lie in the interval from -2 to 5. Well, if that's the case, then -2 is a lower bound and 5 is an upper bound. And we should see synthetically what they just explained in our test up there. So let's give it a try. I'm going to start with the lower bound. I'm going to check and see if -2 is truly a lower bound. So I'm looking at my polynomial, and I see 4, 3, 2, 1, 0, so everything's there. I don't need any zeros as placeholders. And I'm just going to do synthetic like I normally would. So bring down the leading coefficient. You go ahead and do your synthetic. I'll do mine. Let's see if we land in the same place here. No, it must be too early in the morning for me here. There we go. That's better. Everybody seeing the same thing? Now, here's what we were supposed to check. It's a lower bound if our last line of information alternates non-negative and non-positive. Now, that feels really weird that they say non-negative and non-positive, but they're telling us zeros don't have a negative or a positive value. So, non-negative, non-positive, non-negative, non-positive, non-negative. We did it. -2 is a lower bound. Not done though. We wanted to check the upper bound as well, and that was the 5. So again, go ahead and do synthetic. Let's see if we end up at the same place. Let me know if I miffed on this one. So now let's check and see, what did they say had to happen if we're going to see an upper bound? All of those numbers in that last line need to be non-negative. So either positive or 0. They were all positive. So that means 5 is an upper bound. Now this is another thing that was used a lot more before calculators came to be, because we certainly could put that polynomial into the graphing calculator, and we could see that and realize, since it was degree 4, quartic, 1, 2, 3, 4, and we could check the intervals there, and we would see, yes, between -2 and 5. But this is the algebraic way, and remember, that's what this course is about, trying to show mathematically everything that we possibly can. You know, sometimes we have to use the graphing calculator, but most of the time we're using algebra to show that everything's working. So those were our upper and lower bounds. Now, example 7 says, let's try putting all this together here. Finding the real zeros of a polynomial function, which again, major objective of what we've been talking about in this section. And we've got the 2x to the 4th minus 7x cubed minus 8x squared plus 14x plus 8. So now we're saying, let's find them. Let's see what they are. So I start by saying, greatest common monomial factor, nothing I can take out of them all. I don't know how to factor something with 5 terms. So possibles, well, this has an 8 in the back. So plus or minus 1, 2, 4, and 8. And then in the front, I have a 2, so plus or minus 1, plus or minus 2. So that gives me a lot of options. It could be 1 over 1, could be 1 over 2, could be 2 over 1, Could be 2 over 2, but that's 1, and we already have that one listed. Could be 4 over 1. Could be 4 over 2, but that's 2, and we already have plus or minus 2 listed. Could be 8 over 1. And it could be 8 over 2, but that's 4, and we already have that listed. So let me get that comma off of there. So those would be my possibles. Now, I want to narrow it down even further. So I look at this and realize that I'm talking about a quartic that's 4th degree, has 4 zeros. I'd like to find 2 of these, at the very least, in order to work this down in the hopes that I can find them all. So we go to the graphing calculator. I'm going to give you a second to get yours punched in. So there's our 2x to the 4th minus 7x cubed minus 8x squared plus 14x plus 8. Try zoom 6. And I see 4 of them, so I'm hoping I can identify at least 2 and work this down. So second trace, number 2, because it didn't look like maybe 1, 2, 3, 4, 4, 0. Why not? Let's take a second and do second graph. There it is. So there's one of them that's nice and rational, the 4, 0. Gonna need another one. So let's see if we recognize any of these zeros. Negative 1.414214. Now it's pretty rare, but every once in a while somebody recognizes that decimal. Is there anybody that can unmute and tell us what that is? Well, then let's keep going. Second trace, number 2, below it, above it. Oh, we know that one. That one's a negative 1/2. So far we have a negative 1/2 and we have a 4. And we just needed 2 to get us started. So that's where we'll begin. Now, you can use either one of those first. It doesn't make any difference. Most people tend to wait for the fractions, and that's a good idea because the most math is done at the higher levels of synthetic. So I'm going to go ahead and go with 4. 4, 3, 2, 1, 0. They're all there. And let's see what we get. So there's my last line down there. Now, because 4 worked, because I got a 0 over here, and I want to work this down to a quadratic, I can go ahead and continue on using synthetic on the synthetic answer that I just received. So now we're going to do this with a fraction. It's not a horrible fraction, negative 1/2. So you bring down the 2. 2 times negative 1/2 is negative 1. 1 and negative 1 add to 0. 0 times negative 1/2 is 0. Negative 4 plus 0 is negative 4. Negative 4 times negative 1/2 is 2. Hey, we just verified those 2 that we found with the calculator work. But there's 2 more out there somewhere. Let's see where those other 2 are at. Remainder constant xx squared. So most people right away would say, oh, I'm going to factor out the 2. But in the end, this one is faster if we just go ahead and add 4 to both sides, divide by 2, and then take the square root. So that was why I stopped to ask if anybody recognized the decimal 1.414, blah, blah, blah. Because some people do have that memorized as the square root of 2. And we can do synthetic with the square root of 2, just not today. We're trying to do the easier ones. So now, let's see, what did they ask us to do? Because if they said, let's find all the zeros, then we want to write these as zeros. Find all the real zeros. So let's stop and write. We had 4, 0, and negative 1/2 0 that we found and verified with synthetic. And then we have, I'm going to go ahead and write it as plus or minus the square root of 2, 0, because I think everybody can see there's 2 zeros here. Positive square root of 2, 0, and negative square root of 2, 0. So we have all 4. They were all real. We didn't have any imaginaries to work with here. We found them all. So this is what we're trying to get to, finding all the zeros, imaginary, real, whatever they may be, and knowing that we have them all. And it could be, I just want to let you know in your homework, that they might say, find the zeros and write your result in factored form. Now, if that's the case, we want to pay attention to whatever name they gave it. And in this one, it was f of x. And we want to think back to the fact that all of those zeros came from x minus a. So a positive 4 came from x minus 4. The negative 1/2, how did that come to be? Now, you could argue, well, couldn't we just write it as x plus 1/2? But we know that's not what it looked like when it was in the parentheses, so we have to think for a second. So let's see. They had to subtract 1, and they had to divide by 2, because that's how you get negative 1/2. So it must have been a plus 1, and it must have been a 2x in the front, because that's the only way that we would subtract 1 and divide by 2 to get our negative 1/2 that we have for a 0. And then, again, this isn't going to feel real comfortable because we don't tend to factor in terms of radicals. We usually just use integers when we're factoring. But this would be the best way to represent that in factored form. And like I said, I think there's some problems in your homework where they have you take that extra step. So I wanted to show you that. Now, we're still not done with objectives, although the big one we've talked about quite a bit, which is finding the zeros. So we used long division in the division algorithm, and we did synthetic division as well. And we have used the remainder and factor theorems today. We have found the lower and upper bounds. So really, we should have all the skills to do all the rest of these problems. Like I said, we just need to see more. We need as many as we possibly can see together so that we'll feel like we can handle them all on our own. A polynomial function cannot have more real zeros than its degree, but it can have fewer, and here's why. Real zeros. We know from what we saw in Algebra 2 that sometimes we get imaginary zeros, and those imaginary zeros always come in pairs. So when a polynomial has fewer real zeros than its degree, the upper and lower bound tests help us know we did find them all, that we found all the real zeros. So using the upper and lower bound test again. Finding the real zeros of a polynomial function, prove that all of the real zeros of this polynomial lie in the interval from 0 to 1. And then once we've proved that, it says find them. Once you have them, find them. So 10x to the 5th minus 3x squared plus x minus 6. There's no greatest common monomial factor, and we don't know how to factor something that has the x to the 5th and the x squared piece in there. I know it has 4 terms, but it's pretty obvious that if we factor this, it's not going to factor by grouping. So we'll use those lower and upper bound tests. Oops. I'm going to have to put some masking tape over that green so I don't try and use that all the time. Now, one of the easiest numbers to use with synthetic is 0. So this one is missing gobs of stuff. So we've got 10x to the 5th, 0x to the 4th, 0x to the 3rd, minus 3x squared, 1x, and negative 6. And we just want to show that that's going to be the lower bound. So we bring down the 10. Multiplying by 0, of course, gives you 0. Why don't you go ahead and do your synthetic, and I'll do mine, and we'll meet up at the end here. right, so double check everything. Now, remember, and you might have to flip back a page in your notes here, for a lower bound, it said that it has to alternate non-negative and non-positive. Non-negative, non-positive, non-negative, non-positive, non-negative, non-positive. We found it. 0 is a lower bound. Now we need to verify that upper bound by using the 1. So go ahead and do your synthetic. Let's see what we get. So take a peek. Last line there, 10, 10, 10, 7, 8, 2. And again, if we want to know upper bound, you could flip back. And it told us that if we have found an upper bound, that it will be positive or 0. And all of these are going to be positive. So 1 is the upper bound. All right. So now, on to finding them all. Well, again, can't factor this. I could write down some possibles. Here's my 6 in the back. And in the front, I have a 10. So those are all the factors of 6 and 10, the integers that divide nicely into that. Now, I'm not even going to break that down into all the fractions this time, but I'm hoping that when I punch it into the calculator, I'll recognize some of these, remembering that this one had 5 zeros. Whether or not they're all real, we don't know, but let's take a peek. So grab your graphing calculator and go ahead and punch that in while I'm turning things on and off in here. So there's our 10x to the 5th minus 3x squared plus x minus 6. Let's give it a go. Zoom 6, especially since they told us it was between 0 and 1. Well, look at that. It only looks like we get one real 0 out of this. So we could do second table, but we don't see it. There's no 0 in the y over here. So let's try second trace. Number 2, and I'll have to be below it to be to the left, and above it to be to the right. And again, it doesn't matter where you are above and below it, but the calculator has to do calculus to find this 0. So the closer you can stay to the x-axis, the easier it is for the calculator to do that. So now, I see 0.9505459. That's not any decimal for a fraction I recognize. So that means we have to just round it to 3 decimal places, and it's irrational. So, what was it? 0.9510 with rounding. So because we had to use the graphing calculator for that one, we're not going to verify that at all synthetically. Well, pretty close there because I set my timer for 49 minutes. Now, you definitely will be able to finish day 1, and you might be able to get a little start on day 2 as well. But remember, we have 2 assignments over 3 days. So, like I said, definitely you can finish the 1 through 26 now, but when you're getting to 2-4 day 2, if you're feeling like, oh, I don't think we covered one like this yet, hang in there. You know that we still have several problems listed under extra examples here, and we'll get to it. But I know you can probably get a pretty good start on that one too. we're already out of time. Lots of good math, though. So remember, this assignment's on your Schoology update. It's in Schoology, it's in Campus, it's everywhere, so that you can work on those. Have a great day, everybody.